I said 5.
Oh,
I said 7 minutes from now.
Oh,
You took me at that because like you show up in classes before he shows up the ones that teaches, so that's true.
Well, you know, when you beat Professor's son to class, Dr. Keir's son. No, not my professor's son. Dr. Keir's professor's son. Then you've accomplished something. All right.
We all
Standing ovation. Joel gets a girlfriend and thinks he can start skipping class.
Yeah, exactly. You actually be smoking dope.
oh, we're just talking smack about it.
I was in the library upstairs working on a day.
Yeah, Monoy.
Sure.
I don't know what that means.
Joel.
I started at 3.
To me, class doesn't really look like it's.
All right, we're starting chapter next. What's the next chapter? What are we in? Chapter 9 is it we're in? Chapter 9. Wow. Okay. So chapter 9. Discussing phase diagrams.
Yeah, the graphs in this chapter scale you and I looked through it.
Oh, they're easy. Easy peasy. No problem. Let's see if I can black. I think that shows up better for Dan. Okay. So, phase diagrams. This is how we understand how the combination of two or more. Oh, maybe I do want to go back. The combination of two or more materials. Combination of two or more elements. So, for instance, copper and nickel. If I mix copper and nickel together, phase diagram tells me how they behave, primarily as a function of temperature. Okay. So, defining again a phase is a structurally homogeneous region. Well, it's a structurally chemical for that matter. So it's a structurally and chemically homogeneous region. So, if I have sugar and water, and the sugar is undissolved, I have a two-phase system. There's sugar, and there's water. But once the sugar dissolves, it will be uniformly distributed throughout the water, and I'll now have a one-phase system. Yes.
Does that structurally homogeneous mean, like on the test there's a definition of homogeneous or something, I don't know what you call it.
Homogeneity.
Homogeneity.
The property of being homogeneous.
Yeah. So this means that all throughout the entire material, it will all have the same mechanical properties also.
So, structurally, although here we're not so much concerned about the mechanical properties, no. So the structure meaning it'll all be FCC, for instance, right? Because the FCC and BCC would be different structures. Okay. So a phase is a structural, chemical, has structural and chemical homogeneity. So, I've talked before about the Gibbs phase rule. Which you're supposed to learn in chemistry, but apparently you don't. Nobody says anything about knowing anything about it. What's that?
We're still in chemistry, so well, you know.
Who's finished chemistry? No Gibbs phase rule. Did they do Gibbs phase rule?
Well, I remember Gibbs granting it. I don't know. Gibbs phase rule.
Okay.
I think we all did.
Same guy. So F is equal to C minus P plus S. So F is the number of degrees of freedom. That is the number of things you can change and not change the system. C is the number of components. So in the case of the sugar water, there's two. Even if it's dissolved, there's still two components, sugar and water. Okay, copper nickel, two components. P is the number of phases, and S is the number of state variables. Would anyone who's in thermodynamics like to tell me what the state variables are?
Pressure, temperature, volume.
Typically specific volumes.
Yes.
Right? It's pressure, temperature, specific volume. We also have things like internal energy, enthalpy, and entropy, right? But the big ones we've talked about are those three: specific volume, pressure, and temperature. Since most of what we're dealing with is going to be solids and or liquids, right? Then specific volume essentially stays constant. Right? We model those just like we do in thermodynamics as incompressible conditions. So specific volume doesn't change. Pressure, for all of our analyses we're going to consider, is also constant because we're doing this material stuff at nominally atmospheric pressure. Right? We build bridges, we don't build them, to operate in Jupiter's atmosphere. We build, they're operating in.
What do you call it?
Good luck with that. And so pressure is constant. So really, in everything we're going to do in here, the number of state variables is just one. The only thing we can change is temperature. We can't really change the pressure of the specific volume, so we're going to just change the temperature. Okay. But if you were doing it in thermodynamics, Gibbs phase rule would be applied differently because in thermodynamics we're talking about gases where we can change pressure, specific volume, and temperature pretty readily. All right. So consider a pure metal at its melting point. We take a chunk of copper and we melt it. What are the, how many components do I have? One. So C equals 1. How many phases do I have? 2 at a melting point, solid and liquid. Number of phases is 2. And as I said, state variable equals 1. So F equals C, 1, minus P, 2, plus 1 equals 0. That says I have no degrees of freedom. If I change the temperature, I will change my conditions. Right? If I take my T sub m, move away from T sub m, these are all equilibrium assumptions. If I move away from T sub m, make it hotter, what's going to happen?
Melts.
Right, it's all melted, so my number of phases becomes 1. Right, and I change my conditions if I deviate from that location. Okay.
So if anything changes, the condition of copper changes? Is that?
So if anything changes, if I have 0 degrees of freedom, so if I change anything, in particular temperature, because that's the one that's most readily changed, then I will change my set of parameters here. I will no longer be in the 2-phase region. Okay?
So is there such thing as negative degrees of freedom?
Is there such a thing as negative degrees of freedom? No, there's not.
Okay.
So consider a 2-component system. Let's say copper plus nickel with 2 phases. Actually, tell you what, let's not make it copper and nickel. Let's make it something you guys maybe have actually worked with. What's that?
Solder.
Solder. Right. So we make it solder, lead tin now. It's just not we don't use lead tin solder. You got to use clean solder for the labs back here, but we use lead tin solder. So we have two phases present. In other words, solder at the melting point of solder. Right? Solder, there's a particular melting point, right? Okay. So now, C, the number of components is 2, but there's still 2 phases present, and I still have my one state variable equals 1. So I can vary something and still keep 2 phases.
So the degrees of freedom is
telling you how many things you can change before what exactly changes? Like the phase or, I don't know, what else is there?
Right, I can change one of those things. And as we'll see in a second, I can show you, we'll talk specifically about this today or tomorrow or Monday. I think probably Monday we'll talk about lead tensile.
So, we're only, our state variables are only gonna be one in this class.
Right, because temperature is the only state variable that's going to change. Pressure, its specific volume will be constant. Specific volume, because everything's liquid or solid and modeled as incompressible, particularly incompressible at the pressure, the atmospheric pressure that we use in most of our applications.
And then our degrees of freedom, are we talking, or are we need to change it within like a small amount?
Well, it could be a small amount, it could be a large amount.
Because I mean, like, if you change it too much, you're gonna eventually hit.
You'll see as we go through. So what that says is, at that point, I can change the temperature and still maintain two phases. Yes?
Are we ever gonna get more than 2 phases? I guess we could get 3 at the triple, but is that?
Yeah, so we're not gonna, everything we deal with in here will be two phases, maximally, at a given, because, yes, plotting that out, because at best we want to go to 0. If we have 3 phases, we get a negative, what's that mean?
I'm still not really sure what the degrees of freedom means.
It's how many things I can change and still stay
How many
in the
things?
condition.
Like,
I can change the state variable, right? I can change the composition. I can change the distribution of something and still stay at that two-phase condition.
so we could.
So let me draw an actual graph and we'll kind of see it, right? So phase diagrams are comparing these two pieces. Temperature and composition. And we want to see what happens to the phases. Right? They're diagrams showing us the phase as we vary composition and temperature. Does that make sense? So what we end up doing is we plot one of those on each axis. Temperature is plotted on the vertical axis, and composition is plotted on the horizontal axis. But because composition is bound on both ends, we only have 0 or 100%, those are the limits. What we plot is we plot percent B on the horizontal axis. When we have 0% B, it's material A. When we have 100% B, it's material B. Everything in between is a mixture. So the horizontal axis will have units of percentage, 50%, or 75%, and 25%. Plotting percent B versus temperature. There are ternary phase diagrams, meaning 3 different things, A, B, and C, but they're much more complex. They look like triangles, and we're not going to do that. Can't do it, because you're trying to plot too many dimensions. I think it's confusing. So everything we're going to deal with is just a binary phase diagram. 2 materials, A and B. So one kind of binary phase diagram is represented by the combination of copper and nickel. That is a complete solid solution. So I have a complete solid solution, which one do I do? 50% nickel. Pure nickel on that side, and be pure copper on this side. The phase diagram looks like this. If I'm at very high temperatures, what happens if I take some copper and nickel mix it together and raise it to a very high temperature? What will happen to the copper and nickel? It'll what?
They melt.
They'll melt. So here I have a liquid. What if I cool it down to room temperature? A solid. And in fact, it's a solid solution. What that means is I can get a uniform distribution of any amount of nickel in copper. I can take a pure chunk of copper, Stick 3 atoms of nickel in it, they'll uniformly distribute as a solid solution. I can keep adding nickel atoms, nickel, 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 until I have 99% nickel, and it'll still be a nice uniform solid solution. The reason for that is nickel and copper, for all of us who were paying attention on our table, right next to each other on the, remember the little table? The table from your exam? Remember the table at the bottom of the exam, right, where we confused copper and nickel? Right? Copper and nickel right next to each other at the bottom. They have similar sizes, they have similar place on the periodic table. They're very solute, there's a high solubility between them. So what happens when copper and nickel mix, actually, is you get a substitutional impurity. Substitute, the nickel comes in and takes one of the copper locations on the lattice. They're both FCC, it all matches up nicely. Okay. Does that make sense based on what we've learned? Okay. So, we have the solid solution down here. In between, we have a mixture of a liquid and a solid solution. So in region 1 up here, we have 2 components minus 1 phase plus 1 equals 2. We can change 2 things up here in this region and still stay where we want to, in the region. I can change the temperature, or I can change the temperature and the composition, move around, I'm all good. I have 2 degrees of freedom. In region 2, two components, 2 phases, plus 1 equals 1. I can, in that region, I can change the temperature or the pressure, or the composition.
If you change them like together for a rate, couldn't you stay in that position though?
Yeah, so I mean, 2 might as well be 6, right? Because I'm only going to change them one, so in other words, I'm here. If I change my temperature, boom, I'm here. I'm still in the same region. I can change my composition here, right? I can move any one of them at a time. So I have 2 degrees of freedom. I only exercise one at a time. So having 16 degrees of freedom and having 1 degree of freedom, there's not much difference.
So what is the point of that?
Because the point, well, I'll show you the point in a second. Okay. There's this 3, so in region 3, 2 components, 1 phase, 1 equals 2. The key is when we get up here to point 4, right there at that boundary. Now I only have 1 component, right? But now I have 2 phases. It's simultaneously in the liquid and the solid state solution, right? Solid solution. Plus 1 equals 0. I can't deviate from that one. So the idea with the idea of the Gibbs phase rule is to identify the locations where I have 0 degrees of freedom. I have to, if I change composition at this point, right? I've changed it. I'm no longer in. I no longer have something else has got to change.
Yeah. All right.
I change my temperature, something else has got to change. Okay. So what that means then is that if I erase my numbers here. If I have a chunk of stuff and I begin to cool it, right down that temperature, if that's 45% nickel, and I cool it down that line, I start off with a bunch of liquid goo. As soon as I get to this point, I start to form solid solution. Right? So solid chunks begin to appear in my liquid mix. But I'm still allowed to cool the solution. Because I have the degrees of freedom necessary, it doesn't have to exist at a single temperature. It can exist at multiple temperatures, right? So as I cool down, I get more and more solid material until I finally get here to the bottom, and the last little bit of liquid disappears, and now I have a pure solid. But I've undergone a temperature change over that range. So unlike a pure material, where melting temperature is a single point, it only melts at that temperature. If you deviate from the temperature, it's got to be either solid or liquid. Here, and these are technically, by the way, I didn't write this up there. I mentioned it in words. These are equilibrium phase diagrams. 2 L's in equilibrium? 1. 1. They're actually called equilibrium phase diagrams. That's the, the official name. Because these are all done, these are all derived assuming an equilibrium condition. So it's slowly cooling down to this point. And begins to form a solid, and then more solid, until it's completely solid. Yes?
Looking at this, it made me think of this like the phase diagram we looked at before, and there was that range where it could be a gas and a liquid kind of existing together.
Right.
Is that because we had multiple state variables in that situation? Would that be why we were able to have that kind of distribution of that kind of evaporation point?
So,
Because like we had more than just temperature that we were able to change, and we had pressure, specific volume, and temperature that we were changing. Is that why we were able to get that kind of, that point where it was at the same temperature, but as you change pressure, you would get a different?
Right, yes, exactly. Because we walked through the whole Gibbs phase rule discussion there in thermodynamics as well.
Okay. Sorry, I jumped class.
That's right.
My bad.
Out of deference to those who are not in thermodynamics, I apologize for Daniel's excursion into a different area. Anyway, okay. So it begins to form a solid as we come down through there, and more solid forms. So if we pick some point along here, we want to know how much solid do I have at that point. This is where we apply the inverse lever rule that I taught you guys in that other class that shall remain nameless. Draw a horizontal line across there. Okay? The solid that the liquid that exists at that point in time has this composition. So this mixture is a combination, a physical combination of this liquid and this solid. That's what actually exists in the mix.
So the liquid is 25% nickel, the solid is like 70%.
65%
Okay, yeah.
nickel. The solid and the liquid have different compositions. Okay? Because the only liquid that can exist at that temperature is 25% nickel. 25% nickel is, if I had a mixture of 25% nickel, it would melt completely at that temperature. So the liquid that can exist is something that's 25% nickel. Similarly, the only solid that can exist, that can solidify at that temperature is 65%. Okay? So I can find the relative mass distribution of solid and liquid using the same kind of principles that we used before, which is this idea of the total mass being related to each end. So I'm not gonna go into the derivation. I'm just going to give you the rule. So we know that the mass of the liquid plus the mass of the solid is equal to the total mass, right? So that means the concentration of the liquid, right, which is, in this case, the mass of the percentage of nickel in the liquid, times the total mass of the liquid, that equals the mass of the nickel in the liquid, right? Did I see that? Concentration of the liquid, 25%, times the total mass of the liquid, whatever that is, however much of it is liquid, gives me the total mass of nickel in the liquid form. Similarly, the concentration of the solid times the total mass of the solid is the mass of the nickel in the solid form. So the total mass of nickel is equal to the concentration of the liquid times the mass of the liquid plus the concentration of the solid times the mass of the solid. Yes.
So the percentage there is percent weight or percent mass?
It's weight
not
percent, it's weight
molar
percent.
percent?
It is, typically, these are given in weight percent. I mean, you could specify another, so I'm thinking there might
One
be
example in here that has molar.
molar percent, yeah, I was gonna say, I think there might be some that are, so if you look at these, most of them should be weight percent, mole percent, there you go, MgO. So the mole percent is typically given for ceramics, polymers, as opposed to metals. Okay, anyway, but, no, look, I can do the same thing, except I'm counting moles instead of mass. Same thing. So, mass of the nickel equals a combination of those two. Well, that then has to equal the composition of the total times the mass of the total system, right? That's got to be 45% or whatever, times whatever total mass I started with. Does that make sense? That's how I get the total amount of nickel. So, I've got two equations right here, assuming I know what I started with, assuming I know my total mass. I have two equations into a known. I know the composition of the liquid, I know the composition of the solid. So the mass of the solid and the mass of the liquid are the only two things I don't know. Two equations and two unknowns. Again, without going into the full derivation, what we end up with then, is that the mass of the solid divided by the mass of the liquid, I guess I am going into the full derivation, never mind. I'm skipping a few steps, but I'm not going into the whole thing. Is the concentration of the liquid minus the concentration of the total, divided by the concentration of the total minus the concentration of the solid. So that the mass of the solid divided by the total mass, if you kind of carry this forward, again, I'm skipping steps, ends up being equal to the concentration of the liquid minus the concentration of the total divided by the concentration of the liquid minus the concentration of the solid. Okay, again, you're probably not going to follow because I'm leaving out too many steps. Which I can rewrite as concentration of the total minus the concentration of the liquid, just by inverting top and bottom by -1 minus the concentration. Okay. So using those kinds of equations, find the ratios, I end up with this expression. So let's look at what that means in terms of the picture. The percent solid, right? The mass of the solid divided by the total mass. Right? The percent solid, right? Everybody see how this is the percent solid? It's the mass of the solid divided by the total mass. Right? So over here is the solid. It's the concentration of the T minus Cl, that length, divided by Cs minus Cl, that length. It's the inverse lever rule. This side of the lever determines that weight percentage. And if I did it the other way, this side of the lever determines that weight percentage. Does that make sense? So if you when you first come through here, right, at this line, I had very little solid. It was mostly all liquid. I just started to form solid. So I have this little piece divided by the whole length. So you can find out how much solid I have. And the big long piece divided by the only slightly larger length gives me the amount of liquid. So I'm mostly liquid with a little bit of solid. And as I progress down here, this side grows, so the solid percentage grows. And this side shrinks, so the liquid percentage shrinks until I get down here, it's all solid. kind of follow that conceptually. Okay? So the key is just to recognize the inverse of alcohol. Right? The percent solid is that, and similarly then, I could write that the percent liquid is equal to the mass of the liquid divided by the total mass, and that's CS minus CT over CS minus CL. Okay. So we use this to find out how much of each thing we have. As we start talking about microstructures and such, we will, this will become more particularly valuable. So let's look at the example that I've drawn here. I guess we'll bring this. So in this case, the percent nickel, I'm sorry, percent solid solution. Percent solid is this distance, 45 minus 25, divided by the whole thing, which is 65 minus 25. So that's 20 divided by 40, or 1/2. If my numbers are kind of just approximate my horizontal dimensions. It's not quite a half, really. This is probably not 45, it's probably 40. I'm going to rewrite that in a different color because Dan can't see that anyway. So the percent solid solution is now, let's make it 40 instead. 40 minus 25 over 65 minus 25, that's 15 over 40, which is 38%. So it's 38% solid and 62% liquid. Good? Okay. Does that make sense to everybody? Okay, then let me do one more phase diagram. So that's a simple solid solution. That's actually there are very few of those that are actually that simple. Very few phase diagrams that simple. Okay. What's that?
We're going to do complex solid solution.
No. So next we're going to do a eutectic.
Much more complex.
That's not much, but anyway, it's more complex. A eutectic phase diagram.
What does eutectic mean? Is there a definition?
You will find out.
Okay.
I remember if let me get the numbers. I don't remember the numbers off the top of my head, so let me draw them. These are in degree C. 327.5, 232, 183. Okay, what I'm plotting here on the horizontal axis is the percent tin in a lead tin phase diagram. Okay? What do I have up here? Liquid. What do I have down here? It's a little more tricky. It is solid. What I actually have, A plus B, are you reading that out of the book? Cheater. So these side regions here are the solid solution phases. Alpha and beta, I've just made up the alpha and beta. I don't know if it's actually, I don't think it's called alpha lead and beta tin, but These are solid solutions. In other words, what that says is the most tin that I can absorb into lead is 19%. And then it has to be at 183 degrees C in order to, excuse me, in order to get the 19% in. If I try to put in more than 19% tin, or if I try to put in 19% at a lower or higher temperature, particularly a lower temperature, that tin will not evenly distribute itself within the lead. And instead, what will happen is the tin will agglomerate itself into chunks that are separate from the lead. And what I have therefore here is a mixture of A and B, or alpha and beta. I have two different solids in this region.
Is that 232 or 23.2?
232, the temperature.
What's the left side? Are they
327.5. Those are the melting temperatures. Yes. That's pure lead and pure tin.
The 183, is that supposed to be in line with that?
Oh yeah, sorry, the 183 is supposed to be, I didn't draw that very well. That's supposed to be 183. Okay, so does everybody understand that? So if I try to put more lead, if I try to put 30% tin, dissolve 30% tin into lead, what is going to happen at equilibrium is it's going to separate off into chunks of tin-rich region and chunks of lead-rich region. Now there'll be still some tin and some lead in each of those. Right, so the lead-rich region, let's say it's 30%, probably about here, let's say. So this is 30%, right? And let's say I'm at a temperature of 150. That's right there, 150 degrees C. What that says is that there's going to be two regions, alpha and beta. The alpha will be lead-rich material, which contains, I don't know, maybe 8% tin. I'm just guessing off the graph. Do you see that? So the composition of the alpha is represented by this dot. Maybe that's 8%.
What is alpha and beta?
Alpha and beta are just two different materials. So alpha is a lead-rich solid material that has some tin in it. Beta is a tin-rich solid material that has some lead in it. And what I'm saying is, if I'm at 30% tin, and I cool it down from liquid to this point, nice and equilibrium, I'll end up with a mixture of that and this. This is a two-phase region. So that makes sense to everybody?
What's the difference above and below the line connecting alpha?
I'll get to that in a minute.
Why is it a two-phase region, not a two, like, component?
Everything on here is a two-component region. Everything is a mixture of lead and tin, unless you're on one of the vertical axes. Just like over there, everything was a two-component, had nickel and copper both.
So how is that two
Right,
phase?
so all of my Gibbs phase rule things had two for the components until I got to 0.4, which was on the axis. So everything here is a two-component system.
But they're both solids, so it's just one phase.
Right, so what you have is you have a mixture of two solid materials. So you can
Oh,
imagine.
there's different kinds of solids.
Yeah, right, so it's like marbles in sand.
And that makes it two phases.
Makes it two phases. The marbles are a different phase than the sand.
So phase is not solid.
Exactly. Exactly. You have two different solid phases.
So you could have more than 3 phases. Like, theoretically.
On the line, we have multiple ones existing at once, but we'll get to that.
What is that, the 19, the line of the 19?
That 19 is the horizontal coordinate at that point.
Okay, is that,
It is the most tin, 19% is the most tin that I can dissolve in lead at any temperature. and still have it be a single phase of lead. Alpha with 19%. So in other words, there's 19% by weight tin atoms distributed uniformly throughout a lead matrix. But they're isolated atoms, they're not a separate phase, they don't agglomerate together. But if I go to 30% out here, that's too much. I can't do that with uniform tin atoms scattered throughout the lead. And what will happen is the tin will agglomerate together and form chunks of tin-rich region, which we call beta, leaving behind the lead-rich region, which we call alpha. And at this particular composition and temperature, that alpha has this composition, roughly 8%. That lead-rich region has 8% tin in it. And the tin-rich region has this percent, which might be 99% tin. So there's only 1% lead dissolved inside the alpha.
And everywhere else,
No beta.
everywhere else it's some combination of alpha and beta.
So this, at this point, I don't have anything at this point. These regions, there's nothing that exists in here. At this point, I have a mixture of this and this.
And you find the
A physical
percentage.
mixture. Just like over here, right, there's nothing that exists in here. What this is the mixture of this liquid and this solid. The two-phase region is a physical mixture of this liquid and this solid,
So,
whose overall average composition is this.
so we would have a certain percentage of like 8% alpha and a certain percentage of like 99% beta.
Right.
We find those percentages by doing the reverse lever rule.
The inverse lever rule tells me how much alpha I have and how much beta I have. So I have this divided by this beta. So I would have the percent beta is going to equal 30 minus 19 divided by 99 minus 19. So whatever that would be. Again, these numbers are made up because I didn't, you have to pull them off of a
It's not 19, right? It's whatever that.
I'm sorry, no, yeah, not 19, 8, sorry. So that becomes 22 divided by 91, whatever percent that is, that's the percent beta.
So alpha and beta are solids of a certain,
Composition.
are mostly lead and mostly tin solids.
Mhm.
L is a solid,
Oh,
or
L
a
is a
liquid, L is a liquid that is any.
Right, so if I, once I get to the liquid state, right, and heat this up to the liquid state, it's all liquid. It's
So if
just
you
all,
have-
because liquid by definition is all.
So if you have something that's purely solid, it's either all alpha, all beta, or a non-homogeneous combination of alpha and beta.
Right.
If it's something that's solid and liquid, it could be either alpha and some liquid at that
Right.
concentration, or beta and some liquid at that concentration.
Right, alpha plus liquid, and beta plus liquid. And the composition, right, if I'm at this point, at this temperature of, let's say, 220, right, this is the composition, these are the compositions of that liquid and alpha. The alpha is maybe 10% tin, and the liquid is maybe 50% tin. So any two-phase region doesn't, the thing, you know, the point where you're at here, this composition at this temperature doesn't actually exist. Only thing that exists there is a mixture of these two. And if I warm it up, I get a mixture of these two. Only when I get to here do I actually get what it is, which is a 30% liquid.
And that liquid portion is a liquid of a combination, correct?
It's a mixture of lead and tin,
And like
but because they're liquid, they're free to move around,
Mhm.
so there's nothing to keep them in any place, so they're, by definition, homogeneous. Okay, yep,
Are these all empirically?
characterized, yes.
Okay, that seems like a lot of work.
And that's, again, that's a painstaking process, because as I said, it's an equilibrium phase diagram, which means you have to go very slow
Okay,
in order to get everything. You gotta cool it very slowly in order to characterize it. And the easiest way to characterize it is actually just to cool it down and see where, find the liquidus line, right? And then this line we find because the liquid disappears. That's the instant where the liquid disappears. Now, there's something special about this. We discussed earlier. There's that one point there. That's called the eutectic point, since it's eutectic. That is the point where there's an allotropic conversion from liquid to a mixture of solid solutions. Means it all happens at once. Right? So as I cool down through this point, I don't go through a mixture of liquid and solid. I go right from liquid to solid. And the solid that forms is a mixture of that composition of beta and this composition of alpha. So in an instant, I have this uniform liquid, and as it cools, it forms a mixture of two solids that are distinctively different solids.
So is that like what happens when solder dries? It just kind of instantly dries?
Right, and that's why lead tin solder, if you ever look, is labeled as 60-40 solder, or sometimes even 61.9, 38.1, because we're shooting for that temperature, that composition. Because you want a single temperature at which it goes from liquid to solid. We don't want, if we came in here, if we had truly 60-40, we'd come down here, right? It would start to turn into a slush before it solidified. Because little bits of it would solidify as the liquid continued, as it continued to cool. Yeah?
So when solder hardens, it's actually two distinct. There's actually the alpha and beta, but you don't see that.
Right. If you took that solder and polished it and etched it and looked at it in a microscope, you would see it, and we'll talk about that.
So they're not macroscopic, like big old
Right,
clumps
right.
of
Everything
alpha.
happens very on a microscopic scale. So to your eye, you think it's just one big chunk of stuff. Yes?
Those different amounts of like alpha beta, those are equally distributed amongst like dozen.
We'll talk about the distribution of the microstructure in future lectures.
So you mentioned polishing and etching. Are we gonna get to talk about Damascus steel? The swords.
Sure, you should do some research and come in and tell us about Damascus steel.
You're the teacher.
It's a passion for swords. All right. So what that means, so that's why, and the nice thing about that's why we use solder, right? The whole purpose of using lead tin solder is that this melting point is lower than either of those. We could use pure tin solder if we wanted to, right? It would work, but we have to heat it to 232 degrees C. The advantage of lead tin solder is we only have to heat it to 183. So we don't have to heat it as hot to get it to work. Okay. We use pure lead too, but it's 327, yes.
So what happens if somebody comes in, puts the soldering iron on 700 and starts to go at it?
Well, all you're doing is just moving on this line, because the solder's fixed to that composition. So all of it, you set the solder to 700, you're wasting time, right? Because you melt the thing, you gotta let it cool down that much further. Okay. But that's why lead tin solder is advantageous, and using lead-free solder is more of a challenge, because you have to find another composition, right, that allows you to get a pure transition from liquid to solid at one point, so it doesn't get slushy. Right, you want it to occur at a single temperature that's lower than 180, or that's reasonably close to 183. You can't use pure tin at 232. Or silver solder, right? The silver solder there, you're just melting it with silver. You're just using silver, which has a even higher melting temperature still. That's what I prefer to go with.
I go with gold.
Okay, so next time we'll talk about an even more complex phase diagram.
There's more.
Hey, nice to meet you. Yeah, I guess I kind of skipped ahead. We're actually supposed to do the inverse lever rule until next time. But yes. All right.
There's no way it's saying it's going to be slightly different.
Very fast.
Not that long, depending on
It's almost it's like Batman.
how long is it gonna take to get
Well, we're
reaching?
I don't know.
Of course, I was like, I know
This
this
is
is
really
really
weird.
Maybe I'll have to ask them.
Hey, sure to talk about.
It's like a cathedral stained glass with things. Oh, yeah, there we go.
Oh, I like that one.
Wait, what? I wanna see. What is
You
it?
came on a good day.
What do you pass me?
Yeah, and in general, material science is like that. This is a survey course.
I didn't hear you.
A lot of materials are just kind of hit on the surface level.
Don't worry
Not
about it.
quite enough.
Yeah, I
Different
didn't realize
stuff.
you
This thing just
did
beat
until
me.
you mentioned it.
I don't think any of us that are